Welcome to episode 117, Spotlight, Protection of Information at Rest, focusing on Control SC-28. Data at rest refers to information stored on disks, tapes, or other media when not actively moving across networks. Without safeguards, that data is vulnerable to theft, tampering, or exposure from lost devices and insider misuse. Disks leak silently when left unprotected. Physical access alone can bypass all higher-layer defenses. Protecting information at rest ensures confidentiality and integrity even when the system is offline or compromised. The principle is simple but powerful. Encryption and control follow the data wherever it sleeps. Building from that foundation, every organization must classify data first and match protection strength to its sensitivity. Classification defines what information is public, internal, confidential, or restricted. Encryption and access controls should align with those categories. For instance, internal operational reports might use standard disk encryption, while regulated health data demands dedicated cryptographic management and separation of keys. Overprotecting trivial data wastes effort, while underprotecting critical assets invites disaster. Classification is the compass that guides all later decisions, ensuring that protection levels remain proportional, defensible, and consistent across the environment. From there, teams must choose between whole disk and file-level encryption, balancing security with performance and manageability. Whole disk encryption secures entire volumes transparently, ideal for devices such as laptops or servers where all contents require blanket protection. File-level encryption targets specific assets, offering finer control and easier integration with access rules. For example, a database system might encrypt only certain tables containing sensitive records. Each approach has trade-offs. Whole disk is simple but blunt, while file-level is flexible but complex. Combining both often yields the best coverage. The device stays encrypted, and the most critical files receive additional layered safeguards. Databases and object storage repositories deserve special attention because they concentrate large volumes of sensitive data. Encrypt in databases at the column, table, or table space level prevents direct exposure from unauthorized queries or stolen backups. Object storage, often used for media or analytics, must also enforce encryption at rest, typically through built-in service features or encryption gateways. For example, a cloud storage bucket holding medical imagery should automatically encrypt each file upon upload with keys managed centrally. Treating structured and unstructured stores equally prevents attackers from finding weak spots in diverse data layers. Every repository, large or small, must carry its own armor. Backups and snapshots require the same level of protection as primary data because attackers and accidents make no distinction. Backup media often contain the full history of sensitive content, yet are sometimes neglected once moved off-site. Encrypting backups before transfer, maintaining separate key custody, and verifying encryption status during restoration are essential. Snapshots, especially those in cloud environments, should inherit encryption policies automatically. For example, when a virtual machine snapshot is created, its encrypted state should persist. Equal protection across active and archived copies ensures that long-term retention does not become a long-term liability. Key access must always remain separate from data paths. Storing encryption keys on the same system that holds encrypted data defeats the purpose entirely. Instead, keys should reside in centralized vaults or hardware modules accessible only through controlled interfaces. For example, an application server may request temporary decryption rights from a key management service, which logs and approves the request dynamically. Separation of key and data creates layered defense. Stealing the storage alone provides no usable information. This architecture enforces a principle of dual control, where possession of one component never equates to full access. Temporary files, caches, and crash dumps also deserve protection since they often contain fragments of sensitive data in plain form. Many breaches begin not with databases but with forgotten debug logs or unencrypted cache directories. Systems should encrypt temporary storage by default and clear it regularly. For instance, virtual machines can mount encrypted scratch volumes that wipe on shutdown. Developers should also sanitize diagnostic outputs to exclude real customer data. Protecting ephemeral storage ensures that convenience features and troubleshooting aids do not silently undermine carefully designed controls elsewhere. Every byte, even short-lived, matters. Reliable sanitization of decommissioned media prevents lingering exposure after devices leave service. Sanitization may involve overwriting data with random patterns, degaussing magnetic drives, or physically destroying solid-state devices that resist complete erasure. Procedures must match media type and data classification. For example, destroying retired drives containing classified information may require witness shredding and certification of destruction. Incomplete sanitization leaves ghosts of data recoverable through forensic tools. Treating decommissioning as part of the security lifecycle, not a maintenance task, closes the loop between protection, retirement, and accountability. True security persists beyond the device's final use. Monitoring encryption status and drift ensures that protections remain active and correctly configured. Systems change over time. New volumes appear, policies evolve, and manual errors occur. Continuous verification detects unencrypted drives, mismatched algorithms, or policy deviations. Automated scanning tools can report coverage percentages and flag assets missing required encryption. For example, a monthly compliance dashboard showing all storage volumes and their encryption state provides immediate visibility. Monitoring turns static controls into living ones, preventing quiet degradation. Drift awareness keeps protection aligned with intent, even as infrastructure expands and diversifies. When exceptions arise, they must be time-bound and supported by explicit rationale. Legacy systems, hardware limitations, or vendor constraints sometimes prevent full encryption. In those cases, formal risk acceptance must define compensating controls, such as isolation, access logging, and accelerated replacement timelines. Each exception should include a specific expiration date and executive approval. Without time limits, exceptions become permanent vulnerabilities. Documenting them transparently demonstrates that decisions are deliberate, not negligent. Temporary deviations managed with discipline maintain integrity of the overall program while acknowledging operational realities. Evidence provides proof of compliance through policies, configuration exports, and validation records. Encryption settings should be documented, test results archived, and periodic verification reports retained for audit. For example, exporting encryption configuration from storage arrays and comparing it against baseline policy confirms alignment. Logs showing key access and rotation further substantiate control effectiveness. Evidence turns protection into proof, satisfying both internal governance and external regulators. The ability to show exactly how and when encryption was applied builds confidence that data at rest remains under consistent, measurable control. Metrics close the loop by quantifying coverage, failures, and remediation time. Coverage expresses what percentage of storage assets are fully encrypted. Failures count configuration errors or unprotected instances. And remediation time measures how quickly discovered gaps are corrected. Over time, improving trends demonstrate program maturity. For instance, reducing average remediation from 30 days to 5 shows agility and commitment. Metrics translate invisible security into tangible progress. Numbers remind leadership that protection is not static. It must be sustained, measured, and improved continuously to retain its value. In conclusion, Control SC-28 ensures that protection of information at rest leaves no blind spots. Encryption, separation of keys, monitoring, and disciplined lifecycle management work together to defend stored data from theft, loss, or decay. Disks, tapes, and snapshots all share one rule. What holds sensitive information must protect it even when unpowered. By treating encryption as standard rather than special, organizations transform storage from passive risk to active assurance. True peace of mind comes when data rests safely, guarded by design, not by luck. Thanks for listening. For more audio courses, daily newsletters, and more, please visit baremetalcyber.com.